Thank you. And we can start now, Drew. Yeah, hi everyone. Welcome to technical session 2. Thanks for being here. This is our technical session. We have some couple of great talks, but before we move to that talks, let's do some housekeeping. You should be well aware of the usual Zoom etiquettes, which are being displayed on your screen as well. Use the hand raise feature if you want to ask the questions. There is also a Q&A button, and the preference is to ask the Q&A by writing the question. That would be much better. As a moderator, I always prefer when people type in their questions. And for everything else, please use the chat. There is a Zoom chat for discussing anything apart from the questions to the presenters. Also, we are recording, and the recordings would be available. Please note the code of conducts which have been published on the website, and the link has also been put on the chat. Please go through them and please abide by those code of conduct so that we could have a great meeting. So without further ado, let's move to the first presentation. We have Nikiforakis from Stony Brook University, and he has an excellent topic called Good Bot, Bad Bot, Characterizing Automated Browsing Activity. So this is quite an interesting talk. And as a part of the program committee, we want to thank Nick for submitting the proposal and everybody else who submitted the proposal. And let's just move to our first presentation. Off to you, Nick.
Great. Can you hear me?
Yes, Nick, go ahead.
Thank you for having me. So the title of this talk is Good Bot, Bad Bot, Characterizing Automated Browsing Activity. And I'll only be able to skim the surface during these 20 minutes. So please feel free to search the same title later in your favorite search engine and find the corresponding paper that has all the details. Briefly, I'm an associate professor at Stony Brook University, Long Island, New York. And I work in web security and privacy and in network security, a wide range of topics. And the ones that are bolded there, web application fingerprinting, honeypots and deception, and anti-bot technologies are part of what we will talk today. So without further ado, let's talk about bots, right? So bots are programs that interact with websites in automated ways. And if you look at the graph on the right, this company called, excuse me, let me switch to my pen, they're called Imperva. It estimates that only less than 60% of traffic on the web is actually from humans. So the remainder of the traffic is coming from bots, that is automated software that's acting like a human. And we effectively can separate these in benign bots and malicious bots, right? So benign bots are bots that we all very much rely on, from powering the search engine results that we depend on, showing us link previews on social media, all sorts of tasks. But malicious bots use the very same technology to do bad things, right? So this ranges from scraping sensitive information from websites, brute forcing credentials, stealing exposed backup files, and identifying vulnerabilities and potentially even exploiting them on the fly on vulnerable hosts. So if we think about benign bots, the good thing about them is that they announce themselves. So if you see here, we have these two examples, one from Google and one from Bing, and these come from specific IP addresses, and in their user agent, they announce themselves when they say, I'm Googlebot or I am Bingbot. And of course, you may be wondering, okay, anyone can claim that. So let's talk about that. A malicious bot can do multiple things and can masquerade as different parties. So the first strategy the malicious bot can have is pretend to be a known benign bot, right? So someone sets up a bot, changes the user agent to Googlebot or to Bingbot, and then starts scraping the web. And with the hope that websites will allow him to keep going because everyone is afraid of blocking, Bingbot or Googlebot. The good thing is that the defenses are fairly straightforward. So large companies, they publicize their address spaces, and you can also reverse DNS any single IP address that you think is somehow related to their crawlers, and you should get that IP address pointing back to their domains, right? So you can see here our first example. When we reverse DNS this IP address, we get the googlebot.com entry. But in the second one, we still have a bot that claims to be Google. But once we reverse it, it points to a completely different place, right? So we can know that someone is faking. So let's talk about the second strategy the malicious bots can have. Instead of pretending to be benign bots, they can just pretend to be users, right? So they can spoof the user agents of users, pretend to be Mozilla Firefox or Google Chrome. They can simulate user actions by scrolling and by typing. They can go fast or they can go low and slow to avoid triggering various thresholds. And they can use proxy servers to position themselves wherever they want to, right? And so if you look at this example here on the right, you can see that these are visitors on my website from earlier this year. They claim to be a Windows 10 Chrome 87, but if you look at the resolution, it's 800 by 600. So that's highly unlikely, 2021, for someone to be running this as their real system, right? So clearly it's something fishy is going on here. Someone is pretending to be something that they're not. So the defenses are anomaly-based. So maybe timing requests, looking at the types of requests. Are we getting requests for HTML pages but no images because a bot is optimizing? Can we find the IP address in an existing block list and just not serve it any content? And maybe can we throw captchas at clients that we're suspicious of? But of course, we can't overdo it, because if we throw captchas at our users all the time, they'll just go to a different website, right? So this brings us to sort of a problem. We have circular dependencies, right? So we want to build a system for detecting malicious bots. But in order to train the system and evaluate the system, we need a data set of malicious bots, right? But in order to get the data set of malicious bots, we need a system for detecting malicious bots. So right, this is the circular dependency. And prior work effectively was just academics sitting down, looking at logs of web servers that they had access to, and just manually labeling requests as bot, benign bot, malicious bot, or user related, right? And so what we wanted to do is we wanted to come up with a method that would not depend on our prowess of manual analysis, right? So we want to be able to differentiate between benign bots and malicious bots. We want to be able to understand what are their activities of the malicious bots. We want to know what is their actual identity, despite what it is that they claim to be. And we want to also see their trends over time. So to do that, we built a system which we called Aristos. Aristos is a minor god in Greek mythology, protector of beekeepers. And hopefully you will understand why we called it that. So Aristos is a system that provides flexible deployment and management of honey sites. And so what's now a honey site? A honey site is a fully functional web application that exists for the sole purpose of attracting attackers. And instead of just being a typical web application, we have augmented that application with state-of-the-art fingerprinting techniques so that we can learn as much as possible from the clients that arrive on our honey sites. And we pull logs from these honey sites every single day, and then we can later analyze these logs to understand what it is that happened and who visited us. So this is the overview of Aristos. And again, I'll have to skim over a lot of things due to the limited time. So let me tell you first about the honey sites themselves. So like I mentioned, we deployed real web applications. So we deployed real WordPress and real Joomla and real Drupal because we didn't want someone to detect that we're somehow faking our identity, right? These are real web applications running for real. And our choice was effectively to select the ones that have been around for decades and have had hundreds of vulnerabilities and millions of installations. So they present attractive targets for bots that want to attack us. All right. So once users come to our honey sites, then we can actually start fingerprinting them to understand what it is that they support, who are they, right? So for instance, we do JavaScript API support, right? Does this client actually run JavaScript, right? Can we fingerprint the browser and extract various values of it and later corroborate the claimed identity with what we concluded from the fingerprinting? And does this client support security policies? So this is a very interesting technique that I believe we were the first ones to come up with. So we took existing security policies like CSP and we converted them into oracles of a real browser or a fake browser, right? Because if you have someone coming to your site claiming to be the latest version of Chrome, but it doesn't support CSP, well, then you know that this is not the latest version of Chrome, right? And the last one that I'm personally quite fond of is that we're actually also fingerprinting them at TLS layer before the very first HTTP request is sent from the client to the server, right? And so pretty much in the first message from the client to the server when establishing a TLS session, the client denotes what are the cipher suites that it supports. And it turns out that different browsers and different tools support different types of these initialization parameters and different types of cipher suites. So we can really tell, for instance, that this thing right here is actually a program either in Go, right, that is using Go TLS libraries from the signature that we're extracting for it at the TLS layer, regardless of what it states in the user agent, right? And we can do the same tricks effectively for differentiating between Chrome and Firefox and Safari and command line tools, right? So we pull logs from these Aristos sites. We registered 100 such sites. An important consideration was that these sites never existed before. So we didn't want to deal with residual trust issues where we're getting clients because they used to have links to our sites. That's a separate security topic, right? So we registered domains that never existed before. We deployed our honey sites on them across the world. And we recorded all of the information that Aristos sent us over a period of 7 months. And at the very high level, this is what we recorded, right? In these 7 months, we recorded 26.4 million requests that totaled in about 200 gigabytes of traffic, right? And the important thing to always note is that these are sites that no one is using, right? These are sites that do not have any benign traffic. We have never advertised them. So virtually 100% of this traffic is bot related, whether benign bot related or malicious bot related, right? One of the first things that was unexpected for us was that the trend of the number of IP addresses that come to our honey sites per day actually reaches a steady state and continues for the entirety of our experiment, right? So it doesn't like taper off to zero in terms of new IP addresses findings, right? And the number of daily requests also fluctuates depending on whether we're under attack and what kind of attack is sent our way, right? In terms of how the attackers discovered us, we wanted to know if they're finding us via domain names or if they're scanning the IP address space and then finding us like that. And we find that 26% explicitly ask for our domain names, which means that somehow they're obtaining domains that we did not advertise. And we suspect that this is related to certificate transparency, to zone files, and potentially other crawls from a previous from one of the prior attempts. We have this graph here that shows you popular endpoints. What are the most popular endpoints that bots were hitting on our web applications, on our honey sites? And for instance, you can see here that we have a concentration of the WP admin endpoint on the WordPress web application. In other cases, like instance identity, we have almost a uniform distribution of requests. And this is actually, they're trying to abuse a server-side request forage vulnerability because everything was hosted on AWS. And what's important effectively to understand is that this concentration shows that we have tailored attacks, right? So if you see here, these three requests, these three endpoints, they only exist in WordPress. And WordPress is the one that's actually receiving the vast majority, more than 99% of all the requests for them, right? Which means that malicious bots are actually first fingerprinting the application and then sending the payloads that are appropriate for that web application. Right. And so the implication of this is that if you don't run multiple types of applications, you will be missing out on bots that are targeting the ones that you're missing. Right. Somewhat unfortunately and unexpectedly, some of our fingerprinting did not work out as we expected it to work out. Right. So there is very little JavaScript support among bots that are targeting generic websites. Right. So we saw only 0.63% of sessions supported JavaScript, which of course could be converted to an Oracle. Right. You have to have JavaScript in order to use my website. But if you don't have JavaScript, you can't do JavaScript fingerprinting, right? So that unfortunately didn't work. There is this other old technique that says, put fake entries in robots.txt, and whoever touches the things that you're not supposed to be touching is a malicious IP address. No one touched our disallow entries. And we have certain thoughts about that I can elaborate later on. And finally, we had a mechanism that I'll have to gloss over how it works, but we had a mechanism to detect whether there is distributed crawling, where, for example, one IP address scans our website, extracts links, and then a bunch of other IP addresses go and fetch these links. And we discovered that actually, even though large search engines like Google do this, we didn't find any such distributed crawling among malicious bots, which was also somewhat unexpected for us. In terms of classification, you can see here on the left our criteria. Benign bot is a verified search engine bot, a bot that is operated by researchers or security companies. Malicious bots are bots that are sending us traffic, particularly post traffic, and things that we were later able to correlate as vulnerabilities and fingerprinting attempts. And you see here that the majority pretty much of the traffic is malicious. A very, very tiny sliver is benign, and then a large chunk of this unknown traffic that we don't know enough to be able. We didn't see it exploiting us, but it doesn't also belong to anyone that we know of. So that is a question mark and work for the future. So let's talk about brute forcing. So we found that brute forcing was a very common attack, right? So more than 50% of the requests that we received were brute forcing from 47,000 IP addresses. And they were trying very common passwords as well as the domain itself as a password. What was very interesting that we observed is that 99.6% of bots, they issue fewer than 10 attempts at your password before they move on to another website, right? Which means that if you're hacked in this way, you're really using the most horrible password you can be using, right? In this way, the attackers are effectively, spraying and praying, right? Just try the 10 most common passwords, and if it doesn't work, move on to another target. And we had actually observed the same behavior in SSH honeypots in a study that we did back in 2017. We observed application fingerprinting, so you can see here that they are trying to connect to specific endpoints, and these are all related to fingerprinting web application, right? What is this web application? What version is it, right? In order to be able to tailor exploits. And then also specific exploits. We're able to correlate specific API endpoints with specific CVEs that can be quite recent or quite old. And I'll tell you more about this at the end. So we saw 6.7 thousand unique IP addresses searching for backdoors that potentially previous attackers left behind, as well as a large number of searches, 50,000 requests for unprotected, accidentally exposed files, right? Such as a .old extension, a .sql, a .zip, and a .back, right? And a very small number of bots did everything, right? Fingerprinting, attacking, searching for everything. So these are very powerful bots that will just exhaust all of their attacks against you before they move on to their next target. In terms of TLS fingerprinting, this worked very, very well. So we were very happy with this, right? We essentially were able to boil down all of these millions of requests to just 558 unique fingerprints. And you can see here on the right, what are actually the clients that are connecting to us, despite what it is that they're claiming to be, right? There are tools written in Go, tools written in Perl, tools written in Python, and we can tell all of this from their TLS signatures. And an interesting takeaway is that 86.2% of the requests that we received claiming to be from Firefox or Chrome were in fact fake, right? So they were just claiming a popular identity, but they were built using some of these technologies that I mentioned. We had some interesting case studies. I want to draw attention to this table here on the right. So during the 7 months of our experiment, there was 5 CVEs that were discovered. So the vulnerability was released, was announced during our recording period, and then we still had time to see when is it that we will receive our first attack for that very new CVE. And if you look there at the time to weaponize, we actually found that for 2 of these 5 CVEs, we got attacks on the very same day that someone else publicly, like a security researcher, publicly announced the presence of these vulnerabilities in the software, right? And so this is an empirical backing of what Kathleen was saying during her keynote, that if you delay, even if you delay it by a day in this case, you can be in deep trouble, right? And these are not important websites. These are 100 honey sites that no one should be going to in the first place, right? And so to conclude, as more and more software moves to the web, attackers also move to the web, and they bring all their tool set with them, right? And our site's the definition of unpopular sites, and yet we receive thousands of scans every single day and every single month, right? Honeypots are really powerful, and we can retrofit honeypots to our modern web applications. So we can identify malicious clients and then block them on our production servers. And in terms of fingerprinting, right, any minor communication detail of a client can actually betray its true nature. So you can really use that in order to identify what is really the nature of the client despite what it claims to be. So with that, I want to thank you for your attention. I'm leaving there the paper that you can all find later and have a look if you're interested in. And if there's time for questions, I'm happy to take them.
Thank you, Nick. That was an excellent presentation, fascinating findings. And on behalf of the program committee, we want to thank you for this. I don't see any Q&A, and we are exactly on time. So let's move on to the next presentation. Thank you, Nick.
You.
Thank you. So the next, we have Ronald Dobbins from NetScout Arbor, who will be talking about another excellent topic, a year like no other, DDoS in the time of pandemic. So again, a set of amazing, fascinating information coming up your way from our next speaker. Thank you.
Okay, hi there. My name is Roland Dobbins. I'm a principal engineer with NetScout Arbor, and today we're going to be talking about some significant changes in the DDoS landscape that have taken place since the declaration of the pandemic in March of last year. let's go ahead and get started. A lot of the information that's included in this presentation is available as a free download from netscout.com/threat report. It's a free resource for the community, so please feel free to check that out. So moving right along, what are our key findings here? During the pandemic, we saw a record-breaking number of DDoS attacks, more than 10 million DDoS attacks in a single year, which was a 20% increase year over year. We were seeing something like 800,000 DDoS attacks per month, and that equates to something approaching 27,000 distinct DDoS attacks per day. We also saw attacker innovation with some new reflection amplification vectors making their debut for the first time with 3.5 vectors, and I'll explain the half in a little bit. And we also saw a high-profile DDoS extortion campaign that we dubbed Lazarus Bear Armada, or LBA. This is one of the most prolific DDoS extortion campaigns that we've seen to date, targeting 275 different organizations in 40 different vertical markets in across 55 countries, including several countries here in the APAC region. So in terms of our global DDoS statistics, we saw the largest single attack that we observed directly was about 1.12 terabits per second in terms of bandwidth in EMEA. But in terms of throughput, the single largest DDoS attack that we observed was here in APAC, 581 million packets per second. And the worldwide average DDoS attack duration was around 40 minutes or thereabout per attack. And the peak DDoS that we saw was 929,000 attacks in May. With the Lazarus Bear Armada, or LBA, DDoS extortion campaign, as is very common with DDoS extortion, these extortionists use the names of other groups that were known in the mainstream press. They would call themselves Lazarus Group, which is actually a state affiliated group that's not really known for launching DDoS attacks. They would call them Fancy Bear, which is a similar type of organization, or sometimes they would call themselves Armada Collective, which was a DDoS extortion threat actor from many years ago. And they would send extortion demand. They would launch actually a demonstration DDoS attack first to the target, and then send an extortion demand email demanding payment in Bitcoin. And they were very careful to target specific individuals within an organization who would be likely to see the extortion demand and be in a position to do something about it. We believe that they were using primarily LinkedIn to do this. They started off their campaign mainly attacking financial targets and financial adjacent targets like banks and stock exchanges and online cryptocurrency websites and things of that nature. And then they started broadening and going after more vertical markets as well to just about every type of industry you can imagine. And at various points in time, we saw this threat actor leveraging up to 14 distinct DDoS vectors against their targets. And this threat actor performed a lot of pre-attack reconnaissance to identify potentially weak elements in the application and service delivery chain that they would then target with their attacks. From time to time, this attacker would also be very persistent and go after not only the targeted organization, but upstream transit operators as well, cloud providers, even commercial DDoS mitigation service providers. And something that we had predicted at the outset of the pandemic, that the attackers would start going after VPN concentrators. This attacker did that. That was one of the signature elements of these attacks, is that the attacker would always go after the VPN concentrators, because with the wholesale shift to online work and remote learning, this presents a great opportunity to disrupt the everyday activities of the organization, as well as to impede the ability of security teams to respond. And so if we actually take a look here at the attacks over time, you can see they started showing up in Europe, then North America, then here in APAC, as well as in Oceania, which is like Australia and New Zealand and Pacific Islands as well. And so over time, the attack did in fact show up globally. And something that we notice as well about this attacker is that when the attacker was attacking a particular organization, a particular country, country, it would be followed by other organizations in that same country or region, and the attacks would take place during the business day for that particular region. And as I noted before, LBA started out attacking financial institutions and broadened to encompass many other verticals, but still always continued attacking financial institutions on a global basis. And we can take a look at the DDoS vector preference here as well. Over time, we can see that there were some variations here in what the attacker would choose to do, but we always typically saw DNS reflection amplification combined with some other vector or set of vectors as well over time. And here we're able to actually plot the different attack vectors used by this threat actor during the attack campaign. And that's one of the interesting things about this attack campaign is we actually had firsthand experience working with network operators to defeat these attacks. And we were also able to by developing a signature, as it were, for this threat attacker, we were able to actually understand the extent, the breadth, and the depth of this attack campaign over time. And there's a presentation in tomorrow's technical session that talks about that very specifically. Now, moving back to the macro analytical front, here we have a breakdown of different vertical markets targeted during the pandemic, with, of course, wired broadband operators receiving the single largest number of attacks. But something that did pop up here that we hadn't seen before was we've always seen attacks against online news sources and video sharing sites and journalistic sites and things of this nature. But those attacks really skyrocketed during the pandemic. And so that was something that we noticed with the mix of verticals that were targeted. And so when we take a look at the DDoS vectors that were used by the attackers, we saw these 3.5 new reflection amplification vectors: Plex Media, SSDP, which leveraged abusable Plex Media servers as UDP reflectors amplifiers; Windows RDP, which is Windows Remote Desktop Protocol running over UDP again; unsecure or insecure RDP servers were leveraged as reflectors amplifiers as well. We saw DTLS, reflection amplification, which primarily leveraged load balancers that supported DTLS without the cookie option that allowed them to be abused for UDP reflection amplification attacks. And we also saw some attempts to leverage Jenkins, which is a software management and versioning control system, which could be abused in this way. But the thing is, the Jenkins service seemed to be so brittle and fragile and unscalable that attempts to use it on the part of the attackers typically resulted in an outage of the reflectors amplifiers, and the DDoS attacks trying to leverage Jenkins pretty much fizzled. And if we look at the breakdown overall by vectors, DNS reflection amplification was the single most prevalent DDoS vector that we observed. A couple of years ago, it supplanted SYN flooding as the most prevalent vector, and that's continued. We also saw a real upsurge in ACK flooding attacks, and those attacks were very specifically targeting organizations that do financial and credit card processing and other things related to the financial services industry. And of course, you see other reflection amplification vectors as well. We also saw the rise of omni-vector DDoS attacks. DDoS attacks that are multi-vector nature we've seen for more than 20 years, but we've seen a real rise over time of the number of simultaneous vectors used, and the attack with the single largest number of simultaneous vectors used was 25. That's 25 different DDoS vectors being used to attack the same targeted organization at the same time. So that was a huge increase in multi-vector attacks as well. So if we do a regional breakdown here, we saw some significant increases in attack frequencies and decreases across the board in attack duration. Here in the Asia-Pac region, we actually saw an 8% decrease in attack frequency, but we saw this shift to decreased attack duration. And we believe that the primary reason behind this shift in attack duration is due to the real rise of DDoS for hire services or boot or stressor services, which primarily charge their criminal customers based on 5-minute increments of attacks. And so here in Asia-Pac, it's taken a while for the boot or stressors to really come to the forefront of the DDoS spectrum, but we're now seeing them being used here in APAC a great deal, with local language translation options available to make it even easier for criminals to make use of them. And so that's why we're seeing this overall decrease in attack duration. And if we take a look at the simultaneous peak attack bandwidth, we can see here that here in APAC, for example, in September, we saw 2.3 terabits per second of DDoS attack traffic simultaneously in a single 1-minute interval across the entire region, which is quite significant. And then if we take a look at throughput, the same thing. In September, we saw basically elite million packets per second. That is actually 1.3 gigapackets per second of contemporaneous simultaneous DDoS attack traffic taking place within a single 1-minute interval across the entire region. And I don't know about you, but I've never really had a reason to talk about gigapackets per second before. But we're now seeing this in the DDoS threat landscape. And in terms of the multi-vector attacks, again, we're seeing this move up and to the right. This illustrates the increase in multi-vector attacks that we've seen over the last 4 years or so. And the same thing with the multi-vector attacks by country as well. We can see it changing over time. Several countries here in the APAC region are represented, and we saw a lot of this in Europe, of course, but here in APAC as well, with multiple vectors being used simultaneously by the attackers over time. And we actually, in the downloadable version of the threat report, we have individual DDoS statistics and trends from 19 different countries, including several countries here in APAC. And so again, we urge you to download the report and take a look at that. It's actually fascinating reading. And when we take a look at the number of abusable systems that have been compromised and subsumed into IoT botnets, that number is up and to the right as well. And the most popular version or type of IoT botnet we see is Mirai and Mirai variants. Now, that's not the only one that's out there, but by the numbers, that is the single most prevalent type of IoT botnet that we see. And just as Nick was talking about in his presentation a moment ago, brute forcing of embedded credentials that were embedded in these devices by default and exposed on the public WAN interface is the primary way that these devices are in fact compromised over Telnet, over SSH, and over time. We can take a look here and see brute forcing attempts taking place on a global basis. And so here are a set of default credentials as well. And you can see here in September and October, we saw the birth of a new botnet. So apparently some devices that had vulnerable credentials embedded in them insecurely by default from the manufacturer were deployed and or discovered by the attackers with that constant scanning. And so we saw a huge increase in the use of these particular credentials and a subsequent increase in bots as a result of those credentials being discovered and abused by the attackers. And so you can get the 2020 threat report here at this URI. And we also have an interactive service that's completely free of charge, where you can log in and you can actually see live DDoS attack data on a global basis. It's actually delayed by, I think, by about 1 hour, but all the different statistics and things that I'm talking about in this report are available to you as well. You can register the free account, and you can even save different types of searches based on region and vertical markets and attack types and those sorts of things as well. And so that's basically all I had in the summary presentation. So if folks have questions, happy to take those at this point.
Thank you, Ronald. We actually have a question. Mike would like to ask a question. So can we give Mike the access?
You're asking me to do that?
No, I'm asking the next staff if they can help me with that. So Mike, are you there?
I think he's muted. Hi, Mike. If you can hear us, you might want to unmute on your Zoom client. You can also type your question in the chat if you're not able to unmute.
Actually, Q&A would be preferred. Use the Q&A. There's a question in the chat. Ronald, why can't we identify and mitigate these attacks by the ISP? Would you like to take that?
Well, sure, that's a complex question. And so detection, classification, and traceback of DDoS attacks is, of course, very important. And a lot of ISPs have implemented the best current practices where they have instrumented their network so that they can see both inbound and outbound and crossbound DDoS attacks, and they can trace back both spoofed and non-spoofed attack traffic, and that's something that's very important. Unfortunately, there are a lot of operators out there who don't do that, either intentionally or just because they are unaware of the necessity to do so. And so that's why spoofed attacks are possible, for example, because unfortunately we don't have universal deployment of source address validation. That's what makes the very large reflection amplification attacks possible, and spoofs and floods and things like that. The other thing is, again, going back to what Nick was talking about in his presentation, is this constant scanning and looking for devices that can be abused and subsumed into botnets. And unfortunately, we have not seen a real increase in the default security postures for these devices. And so from time to time, whether these devices are sold directly to consumers or whether they are deployed by network operators and they have credentials or other vulnerabilities that can be exploited, we're seeing new populations of abusable IoT devices as well as general purpose computers like servers and data centers as well. And so unfortunately, it is an ongoing struggle. We're globally in the best position that we've been in since the inception of the internet in terms of awareness and the ability to mitigate attacks. But the thing is, we still struggle with having things deployed securely by default and making sure that all network operators do implement the best current practices. And so that's an ongoing educational struggle. It's not really a technical issue. It's more about education and understanding the economic reality that outbound and crossbound DDoS attacks have just as much of a negative impact, if not more, on network operators as inbound attacks from the internet from their perspective. So kind of a long answer, but I hope that partially answers the question.
Yeah, thank you, Roland. Roland, related questions from Indunal. With IoT and 5G, how do you see the attack surface enlarging and the cost incurred in enhancing security of the end devices?
That's an excellent question. And so when you're a broadband access operator, whether you're a wireline or a wireless broadband access operator, and even if you're an IDC operator, you have to take your customers into consideration in your threat model because unfortunately people do deploy devices that are insecure, in some cases unsecurable, and that can be exploited by the attackers. And so with the increase, the order of magnitude increase in bandwidth and throughput that is available with 5G, we're seeing operators around the world really reassessing their defense posture, and they're focusing not only on DDoS mitigation, which is protecting web servers and session border controllers and game servers and their broadband access networks against attack, but also on DDoS suppression, which is suppressing outbound or crossbound DDoS attacks. And so this is a real concern that people have. And something else along with the 5G stuff is a lot of 5G traffic is going to be what we call machine-to-machine or M2M traffic, which is these various automated devices talking to one another. And again, these things are computers, and they potentially have the ability to be exploited. And so taking a look at the default security postures of these devices, testing them to see if they're secure, and if they have insecurities, working with the vendors to get them remediated, and or wrapping network access policies around them that help mitigate the risk of compromise and then abuse and botnets to launch DDoS attacks is also really important, and even more so as we move to 5G.
Thanks, Ronald. Mike, would you like to ask your question?
Yeah. In your presentation, you said that you're also seeing attack against upstream transit ISPs and the DDoS mitigator. Are those victims, or are they just in the way of attacking the actual target? So the target is downstream and they're just trying to basically prevent any mitigation strategy.
Right. So we've actually seen, first of all, we've seen transit operators and broadband access operators targeted directly, like the LBA DDoS extortionists and some others as well, recently have targeted them as specific targets for DDoS extortion. And in the context of the LBA attack campaign, very specifically, we would see this particular threat actor from time to time they would target the endpoint organization, like an enterprise of some sort, or an application service provider in the financial service industry, or what have you. And then when the either the upstream ISP, transit ISP, worked to help defend them, and or they had a commercial DDoS mitigation service provider, a cloud-based provider working to help them, we would sometimes see this particular threat actor go after the upstreams and after the mitigation service providers as well. And we saw this particular threat actor be very persistent like this, maybe about 20% of the time. And we don't know why. We don't know if the threat actor was just flipping a coin, or whether this is maybe a group and one of the individuals was more aggressive and persistent than the others. We don't know why, but it was just and specifically in the context of this presentation, it's because they were trying to defend an extortion target.
Thank you, Roland. Thank you, Mike, for your question. Let's move to the next presentation. We are a little bit over time. So next we have Swapnil Patnekar, who's from Shrestha IT, and he will be deep downing on threat hunting using DNS. So off to you, Swapnil.
Thanks, Dhruv. It seems that I cannot share the screen. Cannot share the screen while the other participant is still sharing.
Roland, can you unshare so that, yeah. Thank you. Go ahead, Swapnil.
There you go. Dhruv, can you confirm if my voice is audible as well as you're able to see the presentation?
Yes, all's good. Go ahead. Swapnil, go ahead.
I'm just hoping that all of you are able to hear me as well as see the presentation as well. Can somebody confirm?
Yes, Swapnil, the presentation and voice both are clear. Go ahead.
All right, thank you. So let me move on. So a little bit about me. So I am the Chief Network Security Engineer and CEO at Shrestha IT. I am also an AppNic community trainer as well. A little background before I get into the meat of the topic. At my day job, among many other things, we implement and manage recursive DNS resolvers along with network security monitoring solutions. These, let me just check if everything is all right. Right. So these recursive resolvers are implemented for enterprise networks. Most of them are on-prem as well as on the cloud. We also have recursive resolvers implemented inside networks of network operators. And we primarily use bind 9 and unbound. So let me begin with David Bianco's Pyramid of Pain. So in case if you haven't read about it, I would urge you to do so. So the gist of it, the gist of the idea is that it talks about the relationship between the types of indicators used to detect an adversary's activities and how much pain it will cause them when defenders detect and deny those indicators. So in the case of indicators of compromise or IOCs in DNS, they are easy and simple to identify, but they also do cause some sort of a pain. In the case of the adversary's perspective, that is, if the malicious domain names are identified and taken down, the attackers need to register new domain names, mostly with stolen funds, as an example. So in the context of network, or primarily of a network, DNS is the pulse of the activity. Everything on the DNS begins with a DNS query. Everything on the internet begins with a DNS query. Domain names are also cheap and used by malware to communicate with command and control servers or mothership. From a defense standpoint, DNS is widely used to prevent access to malicious domain names using response policy zones or DNS firewalls. And atomic indicators in DNS are a great source for threat hunting. When I'm referring to threat hunting using DNS, it's all about finding anomalies. Like in this photograph taken by photographer Mohan Thomas, can you spot a young leopard cub's face? I'll give you a couple of seconds to look at the picture. And anomalies in DNS are of various kinds. So in this presentation, I will cover a few, namely DGAs, that is domain generation algorithms, fast flux, newly registered domain names, and Punycode domains as well. But it's important to baseline your environment. So in the context of DNS traffic, if you're running an on-prem email server, you should see a lot of DNS PTR queries. If it's purely an environment where users are web browsing, then you should see queries like DNS-A as well as CORD-A and CNIM records. But what if the DNS traffic contains NX domain or null responses? Do they point to a security incident? Maybe. But they certainly warrant investigating deeper, as I will share in the next few slides. So what are DGAs? Malware basically connects to its mothership, that is its command and control servers, using a single or a few domains. From a defense standpoint, blocking these domains will cause pain to the attacker, and they will need to repurpose the malware using new domains. Using DGAs, the malware uses on-the-fly generation of domains, which are used to connect to command and control servers. This results in more work for the defenders from a detection and takedown perspective. Fast flux, malware malicious domain names point to rapidly changing IP addresses, where the IP addresses are swapped in and swapped out with extremely high frequency. This makes defense using IP denial listing and takedown difficult. The actual attacker network or C2C sits behind the compromised systems, which are used as a proxy. It's also it's like the fast flux network is like the CDN, but for the bad actors. And from a defense standpoint, detecting and blocking malicious domain name is the key. Punycode is a special encoding which converts Unicode characters to ASCII. And here is a snippet from a recursive resolver system running Unbound. And at the bottom of this slide, you have an example of a Punycode domain. Let's hunt. I'll share a few learnings in the context of threat hunting. For a decently sized network of around 5,000 systems, we implemented a recursive resolver and enabled logging, and barely in a few minutes, we were able to detect an influx of DNS queries from a single IP address. As you can see from the image on the slide, it turned out to be DNS queries for DGA domains. Luckily, the domain name registry had already sinkholed the domain names. Also, stop outsourcing DNS and run your own recursive resolvers. So DNS query logging is great, but it doesn't log responses by default. As also logging DNS responses has an impact on the operational performance of the recursive resolver. But something is better than nothing. While there are other methods to gain visibility into DNS data from an incident response perspective, sometimes you could just enable DNS logging to get a visibility into the DNS activity in the network. From a tooling perspective, in the case of an enterprise network, the other source of DNS data could be network security monitoring, where the packets get mirrored and ingested into a system or a sensor or a cluster running something like Security Onion or a Zeek cluster. Both of them are open source solutions. Zeek can ingest live traffic as well as it can ingest PCAPs and generate DNS.log among other logs. Community ID is a great way to simplify the correlation of logs. Here is another tool which we have used in our threat hunting, and it possibly answers a lot of important questions which are very, very important and valuable. So, as an example, in the DNS activity of a network, when was this domain name seen in the network the last time, right? And also the fact that when was this domain name seen on the web? So Mark Baggett created this open source tool called as Domain Stats, which provides an API which you can run locally and send the domain name to it, and it would return a JSON with answers to these questions. You can also integrate this with a SIEM, where the SIEM can make API calls to domain stats, and it will respond back with JSON output, which is consumed. And if you're using Zeek, there is a Zeek script in there that you can check out. So here are a couple of examples of domain stats. The first one is JSON response for the domain Amazon.com, which was seen by the API, which was sent to the API. The alert says that this is the first time that this domain name has been seen in the network, and also that it uses RDAP to fetch the domain creation date, which you can see under seen by web. The second time we look Amazon.com in the API, we get the last seen by you date. And in the third lookup, I gave domain stats, the top 1 million domains, and you can see that seen by ISC, it basically displays that. One thing to note, though, that large number of CCTLDs do not have RDAP server implementation, but the tool will fall back to using WHOIS. There's another tool which is again an excellent resource from a threat hunting in DNS perspective. And again, this tool is written by Mark Baggett. The tool is frec.py. The tool uses frequency tables to detect entropy in domain names, primarily in the perspective of detecting DGA domains. Last year at AppNIC 50, I had presented on the topic of uncovering badness using passive DNS, which is an excellent method to investigate and map the interconnections in the global DNS. And there are many free and commercial providers which give access to passive DNS data, but they don't provide the context and correlation within my baseline or within my network. A passive DNS tool written by Edward provides this context, and it basically uses libpcap and passes DNS traffic over TCP as well as UDP. Once installed on a recursive resolver, the passive DNS log documents several attributes. Here is a sample output from passive DNS log from my recursive resolver. So instead of the log, this data can also go inside a database. And it stores various parameters like timestamp, DNS client, the IP address of the source, the DNS server, the resource record class, DNS query, and the type of query, among many other things. So based on the tooling, there are a few use cases for threat hunting. So using domain creation date as an indicator, investigate newly registered domain names. Using entropy as an indicator, investigate DGA domains. Using a baseline of whitelisted domain instead of the Cisco top 1 million. And using historical data of passive DNS generated in the network, it enables incident response and network security monitoring. In the context of false positives, when you write custom tooling to hunt for DGAs in DNS data, there were a few roadblocks. For example, Chromium browsers sending junk to the root servers. While reports suggest that this was fixed in Chromium 287, the last time I checked a couple of weeks back, the issue still persisted. So I'm not sure what is happening in that context. So the gist is Chromium, whenever it starts, a Chromium browser, it will send random characters, 7 to 15 characters to check if there is a captive portal in the network. Also, there are certain applications which primarily send DNS queries which appear to be DGAs. From a challenges perspective, our implementations and threat hunting has been using DO53. And we have uncovered a lot of badness in the DNS landscape, which we have reported to Indian CERT as well as companies like Apple, where we uncovered around 400 plus domains impersonating Apple. However, the DNS landscape has already changed, and DNS over HTTPS or DOH is what is going to be the norm. So while DO53 is plain text query response protocol and an ideal friend of the defender, in the case of DOH, the control plane and the data plane is the same. So DO53 provides visibility for threat hunters, whereas DOH hides the existence of DNS traffic. With DOH, how does one identify which session contains DNS traffic and which contains web browsing activity? Right? So a study by SANS Institute puts the lack of visibility into context, as you can see from the image at the bottom left of the slide. So you can see that with DO53, there is a good amount of visibility from a DNS perspective, but with DOH, there is no visibility on DNS. And even at the endpoint, if you're using Sysmon, Sysmon will not log DOH if the endpoint is using DOH. So how does one detect DOH? Possibly inspect TLS. One way could be TLS fingerprinting using JAR3 and JAR3S. NetFlow along with manual heuristics seems to be the way forward. From a community perspective, we publish malicious domain names, which we find in a threat hunting in a DNS response policy zone format. So if you're running a DNS firewall or RPZ, that is, then you could configure this in your recursive resolver. The image basically on the slide shows how to do this in Unbound. We are also running a private MISP instance at this moment and have been a part of the Circle MISP instance. By hopefully sometime soon, we intend to share the threat intelligence with the wider community. A big shout out to all the folks behind these amazing organizations producing quality open source software, NLNet Labs, the folks behind Unbound, the Internet Systems Consortium, the folks behind Bind, PowerDNS, Cannot DNS, Security Onion, and Zeek. Here are references to all the stuff that I've mentioned in this presentation. And if we have time, I'll be happy to take any questions. Thank you.
Thank you, Swapnil. If there are any questions for Swapnil, please use the Q&A or raise your hands and you'll be led to ask questions. We have around 2-3 minutes. Seeing nothing, I would like to thank you, Swapnil. Swapnil, that was a great presentation, as usual. And thanks for all the presenters today. I think it was a very interesting set of talks. And we are really happy for everyone to be here, for our speakers, as well as everybody presenting. I think we will have a Zoom poll now. So I request everybody to give their feedback using the poll. Is session poll? Yes, so I think it has popped up on your screen. Please rate this session. Let us know how we did. That will always help us to do better next time. And now we have a 15 minutes break and hope you guys enjoy your break and see you in the rest of the session. Thanks, everyone. Thank you.
Thanks, Drew, as well. Thanks for great moderation there.
Thank you. Bye.